Hello everyone, today we are going to explore dynamic programming approach and these are the problems we are going to discuss today. So very first problem is longest increasing subsequence using dynamic programming. We will be given with few numbers and our task is to find longest increasing subsequence. So subsequence means something in which order must be preserved and also it it is not necessary that it should be contiguous. If I have 2 3 1, then these are all valid subsequences, but 3 comma 2 is not a valid subsequence because order is not preserved. And here we can see 2 and 3 are increasing number and 1 at 1 it is decreasing, so we will not consider 1. So LIS here will be 2 comma 3 and length is 2. First of all, we will input numbers and DPRA. DPRA will keep track of LIS at a particular position. At ith position I am standing, it will tell me the longest LIS I am forming with my previous elements, and it is set to 1. Why? Because we are assuming at initial state that LIS at each and every position is that element itself, which will be of length 1. So previous array is used for reconstruction of subsequence and it is set to -1 because initially we have no previous element to consider in LIS. Max length is something keeping track of LIS for entire array. And last index, as we are keeping track of previous elements in previous array, but we are not considering the very last element we will get in our subsequence. To note it down, we are using last index here and it is initialized to -1. We are running the loop from 1 to num -1 because at 0th position there is no point actually running the loop, because at the very first position we will not get any value greater than 1 in DPRA because there are no previous element. There is no scope for very first element to form subsequence greater than 1, length 1, and J is running through 0 to I minus 1 because this means that we are traversing through all the previous elements with respect to I. And here we are checking for the increasing order and here we are checking for the increasing subsequence. Is it counting for increasing my elements, number of elements which I will get in my subsequence? If my number of elements are getting increased, then only I will consider. If I am getting two valid subsequences of same length 2 and 2, I will not consider. I have already got subsequence with length 2. Why will I consider another subsequence with same length? So here if I get something greater than this, then I will update this GP that hey, I got some more element to add on in subsequence, and previous I will update with J, means I will tell that I am keeping note that I have got some element in previous element to consider in subsequence, and I am updating max length if I get length of subsequence greater than previously I was considering for whole array. So I will update it accordingly and keep track of last index that is I here, for which I was testing the subsequence. These are the steps to follow for reconstruction. Let us assume we have some LIS linked list and last index we will follow these steps until and unless last index get -1. I am adding number at last index to my first position of LI. My first position, as you can notice that we are starting from backward. So numbers will get reversed, and as this is sequence, order must be preserved. To preserve order, we are inserting elements at first position, and last index updates to previous of last index, and this is the rule of previous array to actually know what was my previous element with which I was forming my alias, and return this alias when it will be formed. And actually there is no need to have this reconstruction part, because alias problem needs to get the longest increasing subsequence length. But to get clear idea, we can use previous array. Let us look at this example. 10243 are my elements, and I will trace how we will get alias in this array. So very first condition was, is it in increasing order at this position element greater than this position? Condition is false. We will move forward, we will do nothing. This iteration will stop because at this position there was only one element present before it. But at this position again we will check condition, is 2 greater than 1? Yes, we will move forward. Is d of j plus 1 greater than d of I? What does this mean? I am checking that I am standing at this position. I am checking for j position, that j might have, this is first element, so it will not have any previous element. Let us say I am at 1, so 1 has previous element at 0th index, so it might have formed some subsequence with this element. So I will consider this value and try to add plus 1. Plus 1 means this ith element and try to find out that does I am counting in increasing the subsequence length, or it is actually doesn't matter to actually add 1. So I will check this 1 plus this another one for this ith position. Is it greater than this previous value, which is 1? We were assuming that at each position there is only one element present as valid subsequence. So 2 greater than 1, this condition is true. We will update dp value to 2 and dp of I to 2 and previous to j. That is, I am noting down that at location 2 I have got some previous element with which I can form alias, and I will check that is my maximum length is changing or not. Previously I initialized it to 0, that considering there was no alias present. So here we can clearly see that 2 is greater than 0. So we will update it, and last index that I actually checked alias was 2, so we will update it with 2. Again I will check for this element 2 greater than 0. Yes, this condition passed, and I will check this 1 plus this positions 1 plus 1 will be 2, and 2 is greater than 2. No, I have already got subsequence 1 comma 2 of length 2. Why will I consider 0 comma 2 with same length? There is actually no point into this. So we will do nothing and move ahead. For this element again I will check 4 greater than 1. Yes, then 1 plus 1 greater than 1, of course. Then this will be updated to 2, and again I will check is max length is getting updated. I have already got length to subsequence actually 2 times already before that, so I will not update it. Again we will check 4 greater than 0. Yes, is 1 plus 1 2 greater than 2. Again I am getting subsequence of length 2. There is no point in doing this again. So here I will check 4 greater than 2. Yes, this condition is true. 2 plus 1 greater than 2 or not. Yes, 3 is greater than 2. So I will update this value to 3, and previous value I will note down that at second position I am getting another longer alias. So as you can see here, how DP of array is working here. Here I jth position I have noted down this I got alias of length 2, and at ith position I am getting another of the. Means this is how we are solving sub problems to actually solve our main problem. This is what DP approach do. So again I will check DP of I is greater than or greater than equals to max length or not. It is 2, so I will update these values again. So again I am checking for this. Is 3 greater than 1? Yes. And is 1 plus 1 2 greater than 1? Yes. I will update this, but max length will not update because I have already got subsequence of length 3. I will check for this position 3 greater than 0 and 2 1 plus 1 2 is not greater than 2, so I will do nothing. Again I will check 2 plus 1 3 greater than 2. Yes. Here first we need to check numbers, by the way. 3 is greater than 2, so we will next check 2 plus 1 3 greater than 2. Therefore we have updated it to 3 and noted down previous index as 2, but I have already got subsequence with length 3. There is no point again considering it. So our last step, that 3 greater than 4, no, this condition is false. We will stop here. As we have checked all the positions and we actually got our alias here. So last index value, as you can see here, was last time updated somewhere here at 3. Yes, at this position last time it was updated. Last index was noted down as 3 and maximum length was also 3. So last index was 3. Is 3 equals to minus 1? No. That means there are no previous elements to this. No, there are actually elements present, so this condition will be false. So add number of last index, means number at this position, which is 4, to first position on this linked list. Then we are updating here last index with previous of last index, means this value is 2. We will move to second position and we will add number at the second position to first position, which is 2, and again we will update last index with 0 here, and number at 0 position is 1, and here I am getting minus 1, that is there is no previous element to this element, and we have got our alias successfully. And this is code for alias, you can see here, which is actually same thing. You can check it out, which we have followed the steps previously, and these are few more test cases to actually test is this working correctly or not. As we have done this problem, we must analyze it, how much space and time it is required. So for input I require O of n, DP array O of n, previous array O of n, so total I have O of 3n. So overall I will need O of n space complexity. Time complexity will be uh, as I am checking all my previous element at each position, so there will be n into n minus 1 by 2 comparisons for this, and time complexity will be O of n square. Let us look at the next problem. Before moving ahead, there is also a better option to do this problem. Better option means in terms of time complexity. We have something called as page sorting, which uses greedy plus binary search approach. You can check it out by this given link. Today we are discussing dynamic programming approach, so we will not discuss it here, but it is really interesting to explore it. Do check it out. So our next problem is that longest divisible subset. Here it is longest divisible and subset. Subset means something in which order doesn't matter, and subsequent is something in which order matters. If we have numbers 2, 3, 1, then 1, 2 will be valid subset, but it will not be valid subsequence. So what we have to do in this problem is, if we are given with few numbers, then we need to check for every a comma b in those numbers, then either a should be divisible by b or b should be divisible by a. For example, I have 10, 5, 7, then we can see that 10 get divides by 5, but 7 is the prime number, so it can't get divided by any of these numbers present here. Therefore, our longest subset, divisible subset, will be 5, 10, which is of length 2. So here is the algorithm. As you can see here, it is really exact copy of the previous algorithm, just difference lies here. Here we are checking for divisibility, not for the increasing sequence. So we need to change only this condition. And another major and important difference between these two algorithms is, we need to first sort these numbers before applying all these steps. Why it is necessary? Because when we have set of random numbers, then we can't be sure which number is smaller, which number is bigger. So it is really difficult to know which number will get divided by which number. So to make things easier, we sort these numbers. This is the only difference between the algorithm which we have seen previously and between this algorithm. And these steps, reconstruction shape, are exactly same as previous. And this is the example 2, 4, 8, 16, 20. We have sorted this number. Actually example is 4 to 8, 20, 60. So we have initialized I and j as we have done earlier, and checked each and every condition as we have done before. Here we are checking whether 4 is divisible or by 2 or not, rather than checking greater than. This is the only difference. And we are updating this value whenever we get the desired conditions. And these are the all iterations. You can have a look at it. Due to time constraint, I will be skipping to it. And reconstruction part is also similar, which we have seen earlier. And this is Java code following the same steps which we have seen earlier. And these are the test cases to check is it working properly or not. Space complexity and time complexity are also same, because algorithm is almost same, just there are few minor differences. This is multi-stage graph algorithm. As the name suggests, it is multi-stage, means the set of vertices are divided into various stages, and the rule is that if I am at ith stage, then I can only connect with I plus 1 stage vertices. So I can't get backward or skip intermediate stages. This is the rule. And our task is to find minimum cost path between vertex, source vertex to destination vertex. So here is an example of 3 stages. We need to reach from 0 to 3, and here we can see 10 plus 2 will cost me more than 5 plus 3 8. So best path will be 0 to 3, which is 8. Here is a 14 node example which has 6 stages in it. So here we have two choices. Either we can follow backward algorithm, or either we can follow forward algorithm. In forward algorithm, we construct our path in forward manner. Means what? We construct our path from source to destination rather than destination to source. In backward algorithm, we construct our path from destination to source. And here I am going to apply forward algorithm. In forward algorithm, what we do is we start from source node, and from source node we check at each stage then that which is the best node to be chosen for the source to destination path. So at stage 4 I will check each node 10, 11, 12 and check for 13 which will be the best one. This is what I will solve my sub problem first before solving my main problem, which is source to destination. This is what DP approach do. This is adjacency matrix of the same graph we have seen earlier. The highlighted values are the values, actual values which are reachable. Means what? Here infinity denotes that these two nodes are unreachable. Means 0 from 0 is not reachable. That means it is already reached. 2 to 1, these all are unreachable. Just these highlighted ones are reachable. Here are the proper steps to be followed. First we will input graph array which we have seen earlier, and number of nodes which are num nodes. We initialize num node -1 to 0. Means what? Last node's DP value to 0. Means what? Cost from destination to destination is 0. Cost required to reach destination from destination will be 0. And next array will be initialized to -1. Whenever I am checking my all nodes, I will need to know what was my next node for reconstruction. When all iterations will be completed, I will be at 0. So for reconstruction I will need to know what was my next node for the path construction. And the use of DPR is that DP of I will indicate me that when I am standing at ith node, how I should exactly reach to destination. How, instead of how, I should say that the cost required for reaching destination. It will note it down. And next is keeping track of all my next element which will be required for it. And cost will keep track of overall cost required for reaching destination. So I will travel from num node -2 to 0. Why -2? Because we already know the position of source node and destination node. What we don't know is about intermediate nodes. Our task is to find out what are those intermediate states will be. So dp of I is previously initialized to infinity, which means we are considering destination is previously unreachable for the particular node. And then I will check all my elements, that means I plus 1 to num node minus 1. So first of all I will check if the whatever next element I am comparing with, is it even reachable for that particular element I am standing at. This is what graph of ij will do. And dp of j means dp of j should not be infinity, means whatever next element I am checking for, is it even reachable for destination or not. If it is unreachable for destination, there is no use going to that next node. This is what this condition means. So total cost will be graph of ij plus dp of j. Means what? If I am at I, first I will need to travel j. So I know from j how much cost I will require to reach destination. This is what this is. And cost, if cost less than dp of I, means here we will initially assuming that it is unreachable. If it gets somehow reachable, or we may get better values in later stages of cost, so we need to update it. So we will update dp of I accordingly. We may get better values at any stage. So also we will update next value with j, where the value gets updated. So this is reconstruction path. We will start with 0th index and add that vertex, and we will travel to next node through next array. We are returning dp of 0 and path. dp of 0 will note down overall cost required to reach destination, from source to destination. As I have told earlier, it means dp of I means over the cost required from ith node to reach destination. So dp of 0 will indicate the cost required from 0 to 13 in our example. So here what we can also do, that we know these vertices are divided in stages. So, and we also know that if I am standing at ith stage, it can only connect to I plus 1 stage vertices. So I can use that information, and I can only travel through those vertices which are in I plus 1. I am naming that number with k. So instead of traveling to num node minus 1, we can actually travel number of nodes which are in next stage of the current stage I am standing at. This will optimize my solution. But as you have already noticed, this is 14 nodes example. So it is really tedious to actually extract those stages, what are and maintaining it. So to make things simpler, we have written an overall loop which will work for each and every case. So here we have started with 12 because we already know 13 to 13 cost, which is 0. So first condition 10 is not infinity and 0 is of course not infinity. This will be true, and we are updating cost, and cost dp of I will be updated, and next will also get updated to 13, and we will continue this till all the iterations we have. As there are too many iterations present here, I will be skipping it. In presentation, I have included each and every iteration which is possible here. As you can see, we are at our last iterations. So this is our last iteration. You can see that dp of 0 is 17, means overall cost required from 0 to 13, minimum cost required will be 17. And now we will construct our path. So here, to construct path, I am at 0, so next of 0 is 3, and also I need to add 0. 0 will be added, and next of 0 is 3. I will travel to 3, and I will add 3, adding 3, and next of 3 is 4, travel to 4, add 4, 4's next is 6, travel to 6, add 6, 6 next is 11, 11, so 11, 11's next is 30. So we will also add 11 and 9, then 13, and here iterations will be stopped. This is Java code for the same steps we have followed. These are the test cases to verify the answer, and as input is a matrix, it will require O of n square, and remaining will require O of n, and therefore overall space complexity is O of n square. And as there are n into n minus 1 two comparisons, the time complexity remains O of n square. You may get better performance with adjacency list. This is our last problem, minimum path sum in a grid. Here we will be given with a grid, and we need to find best possible path from top left corner to bottom right corner, and only movement we can do in right direction or down direction, and number of rows and columns need not to be equal, they can be different, and every visited cell must be included in the cost we are calculating. And we are going to solve it by two approaches, dynamic programming and greedy algorithm, and we will compare the both results and try to conclude which is better over other. So in this example we can see that 1 plus 2 plus 5 will cost me more than 105, which is 6. So I will choose 105 rather than 125. This is algorithm we need to follow in dynamic programming approach. First of all, we will need to input grid array and number of rows and columns. dp of 0 0 will be initialized to grid of 0 0. This is the same logic we are using since three last problems. So for first row, what I know that I need to travel 0 comma j minus 1 to reach 0 comma j. So therefore I am adding cost required to reach 0 comma j minus 1 with the value at 0 comma j, which will give me total cost required for 0 comma j. Similarly, I am doing this for first column, and I am done with initialization of first row and column. Now I will fill other cells. So I will be starting from I equals to 1 to n minus 1, j equals to 1 to m minus 1, because all 0 row and column are filled. So I must start from 1 comma 1. Therefore similarly I must either visit I comma j from I minus 1 j or I comma j minus 1. Means what? If I need to reach this cell, I must either come from this green cell or either come from orange cell. So therefore I will add cost at either of orange cell or green cell to the value at this yellow cell to get the cost required to travel I comma j. This is the logic. And now I will construct my path to travel. So I am starting backward. I am starting from bottom right corner. I have initialized I with number of rows and j with number of columns. So I will first add this pair to my path, and until and unless I reach my top left corner, I will repeat these steps. So if I am at 0th row, I must move left, or if I am at 0th column, I must move up. Because I am starting from my bottom right corner, I can either move left or up. So therefore, when I will reach my 0th row, I can only move to left, and when I am at 0th column, I can only move up. And if dp of I minus 1j is less than dp of ij minus 1, means if green cell value is less than orange cell value, I must move up or I must move left. Means if this value is lesser, I will move here. If this value is lesser, I will move here. This is the overall logic to construct path. And then as we are traveling backward, we are starting from bottom right corner and getting to top left corner. So therefore we need to reverse the path at the end and then return path. Here is an example. This is my grid array provided to me. First of all, I will initialize my first row with the logic we have seen already. So for dp of 0, 1, I have this 10 plus 8, 18, and for this value I have 18 plus 2, 20, and similarly I have filled column values, and these steps are properly written to get more clarity. And now we will fill these remaining cells with the help of this loop. Then at each step we will compare these up or left value. Here between 20 and 18, I can see that 18 is smaller, so I will consider 18 and this my grid value. So sum of these two values I will get 23, and I will continue this for each and every remaining cell. For reconstruction of path, I am starting from this bottommost value. So I have added 2, 2 bottommost value to the path. You can see here, and then I will check is it 0th row or column. It is false for now, and I will compare top value or the left value. So here we can see 20 and 22. 22 is smaller, therefore I will move to left. So next pair should be added is 2, 1. Then again none of them is 0, so again I will compare 21 and 23. Again 21 is lesser, so I will add 2, 0. Again we can see now I have got to 0th column, so I will move up, and still I am at 0th column. I will move up and I have reached my top left corner. So these all indices are recorded in path, and as you can see these are in reverse order. We must reverse this path, and this is our required path, and this is highlighted here in grid also. and you can see that at dp value 2 comma 2 I will get the overall required path cost, which is which will be minimum. And now this is greedy algorithm. In greedy algorithm we are not starting from bottom right corner, we are starting from top left corner. So we will start from 0 comma 0 and add and check whether it is bottom right corner or not. Until and unless we will repeat these steps. If we are at last row, then we will move towards right. If we are at last column, we will move down, and again we will compare neighborhood value at in our grid and move accordingly. Whichever will be smaller, we will move accordingly. Either right value or down value will be smaller. If right value is smaller, we will move towards right. If down value is smaller, we will move to down. Then we will add this to I comma j pair to the path, and as we are constructing it in forward way, we will not require it to reverse it. So the path we will get it here will be the final path. And to calculate cost required, we must follow the path we will get here. And now this is the same example we have seen earlier. Now we are starting from here 0 comma 0 and we are now comparing. It is neither last row or last column, so we will compare 8 and 10. Here 8 is smaller, so we will go here and add 0 comma 1, and for 8 we will see 5 and 2. 2 is smaller, we will move to 2, and again we will see we are at last column, so we will move down, so we will be at 100 and from 100 to 2. So this is what the path is followed, and this is the path we noted down. This is actually algorithmic step wise. I have shown how we get the path. So here is the comparison. In DP approach we get sum 24, and in greedy approach we get 122 as a sum. Here you can see how much the approach matters. Here there are various aspects these two algorithms differ, like decision, where should we move. This algorithm decides very differently. Means what? Dynamic programming solves sub problems to get solution of the main problem, but greedy algorithm looks for the only for local value. It do not consider overall situation. In this case we can't guarantee optimal solution from greedy algorithm. You can see that from 24 we are getting 122 for one the same question. Here we are not dividing it in any smaller pieces like sub problem or like that, and there is no backtracking for it, and also there is efficiency problem in it. And of course, as we are following different approaches, we have got different path, and also result difference is significant. Here is the code in dynamic programming approach and greedy approach as well. You can look at it, and these are the test cases. Here space complexity for input DPR and path will be m into n, and for path, as it is a single array, it will be n plus n. So overall complexity will be O of n into n. Time complexity is also O of n into m, because at each step we are checking either top or left for constant work in dynamic programming approach. These are some real world applications of the problem we have seen today. You can go through this. I will provide presentation in this video. This is Git repository. You can also refer this for more information, and this is my contact email address. You can always contact me. Thank you.